Good morning. It's Guilherme Schardong. Don't worry. I'm going to present our work. We've been developing for a very long time. Actually, it's a high-resolution detection of Earth structural heterogeneities from seismic amplitudes using convolutional neural networks with attention layers. Okay. Basically, this work, I don't know, I'm going to talk more about the problem because I'm not sure how familiar most of you are with petroleum engineer. I'm not. So I worked with in this project. I worked with brilliant petroleum engineers and they did most of the geophysical part, but they tried to make me understand the problem and it helped when solving it. So when I ask you, how do you imagine an oil reservoir looks like? Like, I believe that most people, like myself included, about around 6 years ago, would imagine just a big pool of oil underground, and then extracting it is just like digging and doing like digging a well, like inserting a straw and just sucking it up, right? That's a fair assumption. You wouldn't be wrong. So wrong. Actually, the oil reservoir is more like, at first, it's not just oil, it's mixed with sand, brine, water, gas pockets, which can be deadly if you don't know about them, and a lot of things. And it's not really concentrated in a big pool. It's more like a network of tunnels that are the geological faults and fractures under the earth due to seismic activity. So to extract the oil from these places, for instance, we need to first map these areas using seismic sensors and sound cannons. And afterwards, we need to have a lot of people with geophysical backgrounds to map this area, find the interesting places where there might be oil and there might not be oil anywhere, and to start planning on how to dig those wells to start extracting the oil and the gas and whatever is mixed in there, okay? So that takes a lot of time, a lot of money. Think about billions upon billions of dollars for one reservoir. Okay, so if you do a wrong mapping, if you dig a well in the wrong place, that's a lot of money burned. Okay. So first, our idea is actually a very simple one, trying to help the geophysicists to map this network of tunnels where there might be oil so that they may actually plan how to dig their wells and get the maximum amount of oil possible from under the ground. Okay. So this is a kind of image that we have. This is a seismic image, I believe, from the North Sea. It's a public data set, one of the very rare public seismic data sets. And to me, this is just noise. Okay, I don't know how to interpret this very well. Someone with geophysical knowledge might know, but here we can see some features like this big line here that's kind of a crack under the earth. These cracks are exactly what we are looking for. And it's surprisingly hard to actually find them in an automatic manner. Some of them are very, very small. These cracks are where the oil flows. If I can dig my well to accompany this kind of crack, usually I'll be able to get the oil more easily out of under the earth. So I need to find these in a semi-automatic manner. Okay, so I still need a geophysicist to interpret this. So this here, for instance, is what the geophysicist mapped as a possible location of an oil reservoir. So it's not a big pool of oil, it's kind of this. Okay. So we have, this is like the kind of thing that if you improve 1% the output of your oil wells, you get like hundreds of millions of dollars a year in profit. Okay, so every single percent counts. So the idea is that this is a lot of work. We need a lot of data to train. And as you can imagine, oil companies are not really big on sharing the data, either with the public or with each other, because even if it will help your overall goal, it's still kind of a very hard competition. One of the most profitable businesses in the world is a well-managed oil company. It's like literally getting money out of the ground. Okay, I'm not sure if that still holds. Okay, but it did like 6 years ago. And the idea is that we need to help the geophysicists to get that to make that correct interpretation, to help the people that will plan how to explore that. And that's a lot of manual work, a lot of data, a lot of noise. Oh. And there are a lot of works that try to tackle this. Most of them try to use a mix of synthetic data, which is a very simple model, and transfer learning for like to try to apply this to real world data sets. Problem is, seismic images from different places of the world are very different. Transfer learning is a very hit or miss in this case. And we have like recent models that are like huge transformer architectures that need a lot of data, that need a lot of training, a lot of labeled data, and this takes time. I'll skip the related work session here because we have like 2 minutes. So our idea was like put a very hard foot in the brakes and say, well, why can't we use simpler models like convolutional neural networks with self-attention again? And try to see how we can improve this, okay? And we use the same approach of using static data and transfer learning to try and make to have more data to generalize, train, and then generalize to other types of data sets. And our input patches are like 44 pixels in the direction. And we, with the help of a geophysicist, we were able to train on the F3 block, that's a seismic block from the North Sea, and then generalize it to a block in the New Zealand basin. Okay, this is also publicly available. And our model, even as simple as it is, outperformed even the transformer-based models by okay, it's comparable, it's not a large margin. Here, these are the models published in like last year and last 2 years. The intersection of reunion of ours was slightly better, but we had a much better F1 score. And it's okay. And basically, even simpler models, given a clever application, can still outperform very large transformer-based architectures. We can use transfer learning, we can use synthetic data sets. And I'm sorry, I had to run a lot. These are some of the results we have from a geophysicist RL model. Okay. And we found a lot of fractures and faults here. We can talk a little bit more in the poster session, I'm sorry. But this is basically, even older models can still outperform much sophisticated ones, given the correct tweaking. Okay. And thank you very much.
We have time for a couple of questions. Questions for presenter? Question? Any question?
I have one. So yeah, you were saying that it's very difficult for the humans to look at those cracks because
yes.
They can be very small.
Yes.
And has there been any type of work that tried to look at this from different perspectives, like for example, translating that into signal and analyzing signal, for example, and that would improve the results? Do you know anything that was in that line of direction?
Well, that signal that we have here, this is I'm going to try and explain what I understood. Okay, this is actually a signal that is in the time domain. This is like these are the layers of soil where a very powerful sound cannon was detonated, and then some very powerful and sensitive microphones very far away got this. This is like almost a sonar of the Earth. Okay, and this is mostly converted from time that it took, it's like a radar, back to depth. Some of the work, we are kind of limited, but because these kinds of data sets are very expensive to acquire. And usually, for some reason, our oil companies are kind of short-sighted in this, and they discard the time, the original raw data, because it's like terabytes upon terabytes of data. And then they keep these depth-only representation. This is kind of very low resolution to get some of the more important things. So we're kind of limited for resolution as well. But I'm not sure, other than like spending a lot of money to get better data sets, I'm not sure if there is another work to try and improve this, okay? Yeah.
I was wondering, because you said that right now, what you do is predicting on a pixel level the classification of each pixel, right?
Yes, region basically, yes.
So has there been like I mean, looking at from an outsider perspective, they look very sort of geometrically consistent. So I would think that fitting splines or something around graph prediction might work better in this case.
One of the works here is actually, I had to skip it, but one of the works here is actually a graph neural network for this. And one of the problems is that they still kind of not really solve the problem. You still have very little available annotated data. And these models are usually slightly more complex. So it's kind of hard to scale them as well. But yeah, it's a viable, once we solve the data availability problem and the computational problem, it's a very good alternative as well. Yeah.
Next question.
Yes.
In this type of data, like the geometry of the acquisition actually matters a lot. Like the sources and the sensors are placed like according to a geometry, some distances and this kind of designs. Do you know like what type of geometry are you using? Are the sources regularly spaced, or and how does that affect, or do you think it would affect your model?
Well, I'm not really sure about distances, but what I know about the acquisition system is that basically a bunch of one chip with a really powerful sound cannon that's actually terrible for the environment because it kills everything in the area, everything. And kind of far away, they have a huge grid of microphones. I'm not sure about the size, but several kilometers away. And then when they detonate this cannon, the sound waves go under the earth and then they start reflecting because of the properties of the soil. But I'm not really sure. They have a huge grid of microphones, but I'm not really sure about size or about regularity in the sampling. I'm sorry, I don't.
For marine acquisition.
Yes, for marine acquisitions mostly, yes. I'm not sure about ground acquisitions. I think they use TNT for that, not sound cannons with literally explosions.
Okay, thank you. Thank you.